అరుణ గారు అన్మ్యూట్ చేసుకోండి.
ఎస్ సార్.
అరుణ గారు హ్యాండ్ రైజ్ చేశారు కదా, అన్మ్యూట్ చేసుకోండి. సాగర్ సార్, గుడ్ ఆఫ్టర్నూన్.
గుడ్ ఆఫ్టర్నూన్ సార్.
సాగర్ గారు.
Yes sir. Can you hear me?
Hello.
Can you hear me, sir?
Yes sir, yes sir.
Okay.
Good afternoon, sir.
Good afternoon.
We have another 10 more minutes to start, sir.
No problem, no problem. I'll wait.
Okay, thank you, sir. Sagar sir,
Yes, sir.
shall we start, sir? Or shall
I'm
we
ready.
wait for- Ready, sir?
Yes.
Only one announcement for all the participants. I welcome you all for the day 3 of the workshop on data science using Python. So today, I have sent you an email regarding your registration for this workshop. You can check your email, and if you have paid and your name is not in the list, then you please revert back in that email so that we can make the corrections and all and send it again. And another one is feedback link will be posted between 4 to 6 p.m. on any time we can post the feedback, and it will be opened only for 10 minutes only. And please post only your questions related to the topic in the chat box. Other than that, please avoid all unnecessary messages. And thank you so much. And Sagar sir, you can continue with the session, sir.
Thank you, Kiran sir. So welcome to day 3. Good evening, all. We have a very jam-packed day today. There is a lot of stuff that has to be covered. So without any further delay, let's jump into it. A quick glance of what we are going to see today. We would start with the data visualization. We couldn't cover it yesterday. We then move on to exploratory data analysis using different types of charts, graphs, etc. So EDA, in short, we call this as exploratory data analysis, is to understand the data, understand the relationships in the data. And finally, we jump into our very first algorithm, which we are going to use to make some predictions with some small playful data set that's going to be a linear regression. So that's the agenda today. To continue with where we have left yesterday, at the end of the session, a few people asked about how to handle missing values. Let me complete that by taking quick 5 minutes. Then I'll start with all the basics of data visualization. So if we look at this data sets that we have, remember we read 2 data sets yesterday, one about the automobiles, the cars. So that's this one. And the other one, Titanic data, where we have information about all the passengers who traveled on Titanic on that unfortunate day. If we want to know if there are any missing values in a given data frame, a missing value is something like a null value in terms of database terminology. So you have a table. In that table, you have a column called age. And for some of the observations, for some of the people, we don't have age. So it's just left as blank, and you call them as null values here in the database terminology. And that's what we are referring to as missing values. I can share these data sets with all of you. Once we end the session, I can zip all of them and share it with CIET management. Maybe Kiran sir can share it with you guys. Yeah, no problem at all. So we want to see if there are any missing values in the data. Some of the missing values are very problematic for us in our analysis. So we do not want to have missing values. We want to replace them. If a value is missing, we are going to replace them. And this particular task in data science is called as imputation, replacing a missing value, and that's called as imputation. So that imputation is going to be performed on the columns which has any missing values in it. So if we look at the automobile data set, my DF2, so this is the automobile data set. On this, I'm applying a function called isNA. In Python, missing values are referred to as NA. NA means not available, or another form of NA is not a numeric. So just to show you, you can see here in this data, for cabin, you have a value called NAN, capital N's and small a in between them. This is not a actual value. The value was missing, but when we created this data frame by reading the data, Python replaced this with NAN, and NAN stands for not a number. So not a number is considered as missing value. So you could see that as NA or NAN. So that means those values are not original values. Those values are missing values, and Python replaced them in place of those missing values. To find out which of those columns has missing values, we have a lot of columns, right? We have manufacturer, model, displacement. In other programming language, you would probably have to write a loop, take one column at a time, check if there are any missing values in that particular column, count how many of them, and that's typically the process to find the missing values. But in Python being the most user-friendly language, programming language, you have all of these tasks built in with so simple and easy to use syntaxes. So my df2 is a data frame. On that, we are applying the function isNA. Now, isNA is a function that would always return a true or false. For each element in this data frame, let's say if there are 10 rows and 10 columns, 10 by 10, there are 100 elements in the data frame. It takes each element, checks if that element has missing value. If it has missing value, it will return a true. If it has a proper value, it will return a false. So it would return another data frame or a matrix with 100 true or false values. And I don't want to look at it as a matrix. We are simply applying a function called sum on top of it. Now what happens is, for each column, manufacturer is a column. In the column manufacturer, are there any missing values? If you see 0, that means this column does not have any missing value. Model doesn't have missing value. Displacement doesn't have missing value. Every column in this data frame has a value of 0. That means there is no missing values at all. Second, going with the Titanic data frame, my df, we are applying the same function isNA on it and sum it up. Now if you see passenger ID 0, no missing values, survived 0, no missing values. Look at the age. Age has 177 missing values, and cabin has 687 missing values. Embarked has 2 missing values. Age is a column. Out of the 891 rows we have, 177 rows doesn't have a proper value, and that's missing. So that's why you see 177. Out of 891 rows we have, 687 rows doesn't have a value for cabin, and that's why it is being printed as a missing, counted as missing over here. Now we know that these are the missing ones. There is a function isNA, and you can also use isNull. Both will work in a similar way, exactly same output. So either you use isNull or you use isNA, doesn't make a difference. A caution here, we especially pay more attention to missing values for numeric columns. Age is a numeric column because age is a number, right? It's a float. We can measure it. Now, this is a numeric column, and we do not want any missing values in the numeric column. But cabin is actually a character column. Cabin like C1, CA, there are different types of cabins. So this, though this is a missing value, but this is not in numeric column, so we don't really worry about it. For cabin, wherever it is missing, we could probably replace that missing value as other because are unknown. We don't know the cabin, so we just replace them as unknown. But for numeric columns, we cannot simply replace it with something. So we need to do something. Okay. Generally, in the imputation, whenever a value, numeric column has a missing value, we replace it with mean or median, common replacement. Now, age underscore mean is equal to np dot age numpy, np dot mean. NumPy is the package, mean is a function within this package. Our data frame is mydf, and in that we have a column age. So compute the mean of the age. I can print it for you. So print age underscore mean. So the mean value computed for age is 29.69. Now I'm going to replace all those missing values in the column age with 29.69. So wherever age doesn't have a value, we would replace that with 29.69. Let's see how to do it. MyDF, again, what is the column that we are going to manipulate? I'm going to manipulate my column age. How are we going to manipulate this column? MyDF age. So that means I'm going to perform an operation on this column, fill NA. So this is a function. Fill NA will fill all the NA values. NA values are missing. What do we want to fill with? We already computed. We computed age underscore mean. So we are just going to replace all the missing values in this column age with the computed age underscore mean. Now, once we are done with this step, let me rerun the same step after this. Now, when you run this, for the column age, it became 0. There is no missing values any further in this column age. Why? We replaced it. We filled all the missing values with the mean value of it. So whenever some value is unknown, the easiest way of trying to impute, trying to replace them is just by going with the mean of that variable. Okay. So your Jupyter notebook opens a notepad and doesn't launches. Maybe I have to see what the issue is. We will see. We'll take that later, maybe offline. Okay. So that's missing value imputation. Yesterday, someone asked about it at the end of the session, and we definitely discussed it quite some time. That's good enough for us. Now, let's move on to the next topic, data visualization. In the data visualization, it's all about trying to understand the data, trying to represent the data in the form of plots and charts. For example, there are a lot of plots. What type of plot to use with a given data? And what do we read? What do we understand from that particular plot? So this is called as the anatomy of visualization. What is the right chart for a given data? How to read it? What information can we get it from? What information can we understand from the plot is very important. There are a ton tons of different plots that exist. I would not be able to talk about all of them. So we would maybe start with simple ones, the common plots that we typically use in analysis. One is histogram. The next one is box plot and bar chart. So these ones we use with one variable, or you can also call this as one-dimensional plots. Of course, pie charts are there, a lot of them are there, but I'm going to talk only about the ones that are heavily used. Second, two-dimensional ones. In two-dimensional, we would have box plot again. We have bar chart again, and we have scatter plot. Other plots, we are not going to talk more in detail. Now, first, let's see what is a histogram. Histogram has to be used with a continuous variable. So these are the rules that we should follow. We cannot just randomly go and make a plot out of a given variable. Not at all. We should follow the rules so that we get meaningful insights out of the plots that we have generated. So what is a histogram? Histogram is called as a distribution plot. So if there is a variable like age 0 to 10, 20, 30, 40, 50, 60, 70. Let's say in our data we have age ranging from 0 to 70. We want to break this into bins. 0 to 10. How many people are there in the age group 0 to 10? 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60, 60 to 70. So the height of these blocks that you see will reflect the frequency. The frequency is on y-axis. So if we have total 1,000 people, maybe 0 to 50 we have around 50 people, and this is 100, this is 200, and this is, let's say, 300. Between 0 to 10 we have 50 people, 10 to 20 we have 100 people. So the total sum of this would come to be 100 observations. So this is typically called as histogram, and you can read about it. Where do we use a histogram? We use the histogram along with a continuous variable. And what does a histogram convey? What insight we get out of the histogram? It is the shape of your data. Generally, if we go by the statistics, there are different types of shapes that can exist with the data. We call them as distributions. There are different types of distributions: a normal distribution, uniform distribution, some exponential distributions, etc. Right? So the histogram will always reveal what's the distribution of your data, what's the shape of your data. If you see a bell curve shape like this, then it's called as normal distribution. And if you probably see a graph something like this, which is just keep going on, then it's called as the exponential distribution. It's just keep increasing, like our COVID cases. There is no end to it, right? Now, if you look at some distributions which is like this, which is always going to have a constant magnitude, so that's called as uniform distribution. Maybe talking about distributions would take a lot of time. I'm not going to spend that here. So a histogram tells you how is the data distributed. Is it normally distributed or not? Next is Boxplot. Boxplot is more for statisticians. It comes from the statistical concepts. It's called as Whisker Plot, and you would see something like this. There is always an x-axis. Let's say if we have age, the least age that we have is 2 years. The median age is 25 years. The median is this line. It's called the 50th percentile. This is the 25th percentile. So wherever this touches your y-axis, this is your 25th percentile. This is your 75th percentile. And these upper ones and lower ones are called as whiskers. So this is the lower limit of your whisker. This is the upper limit of your whisker. Sometimes in a box plot, we would see something like this, where you would probably see some dots on the above or some dots on the below. So these kind of dots reflects there are some outliers, extreme observations in the data. So with one single plot, we can infer how is the data values distributed. So this is your 25th percentile, 75th, 50th percentile, the upper whisker, the lower whisker, are there any outliers, etc. So that's why this is a very, very useful plot for data scientists. And you make a note of these plot names and try to research a little bit more about these plots. You would be able to understand them. These two both continue, these two, histogram and box plot, is for continuous variables, numeric variables. Bar chart is for discrete data, where you have character data. Let's say out of the 1,000 people that we have, how many of them are males? How many of them are females? Let's say this is the count for males. This is the count for females. You have a y-axis here, which says 650 of them are males, and let's say 400 or 350 of them are females. Now the height of the bar will suggest the count of the people that we have. So this is a bar chart. There is a very good similarity between a histogram and a bar chart. But if you notice, histogram is for a continuous variable, and for a histogram, there won't be any gaps between these blocks. We call them as bins. We don't call them as bars. So these are bins. But for a bar chart, this is discrete data. So they will be very much separated from each other. Even because of the space issue, sometimes you might see a bar chart like this, where there is no space between them. So this is male and female, but still it is discrete data for us. So bar charts we use with discrete data. Okay. A presence of an outlier is a concern for us. We will talk about it in linear regression. Okay. Boxplot just tells us that if there are any outliers or not. But what would be the problem if we have an outlier? We would have to discuss with each and every topic. Okay, it depends on what type of analysis that you are performing. Presence of outlier is not a concern every time, but yes, depending upon what analysis we are doing, presence of an outlier can influence your analysis. Boxplot, again, this is two-dimensional. Okay, we have more than two variables. So when do we, let's say we have the weight of individuals, and we are looking at the distribution of weights, and we are trying to look at the distribution of weights separately for male and female. We have a y-axis. The weight starts from, let's say, 40 kilograms, and it goes all the way up to 100 kilograms. So the median weight for males is, let's say, something like 70 kilograms, and the median weight for females is, let's say, 62 kilograms. So this tells us, hey, there is a slight difference between the distribution of weight between males and females. When these two boxes are exactly parallel to each other like this, now there is no difference between males and females when it comes to weight. But when you see, let's say instead of weight, if we try to plot the heights of males and females, so the distribution of height in males and females would be looking like this. So this is your male group, this is your female group. Males, let's say, starting from 5 going all the way up to 6.5 with a average, with a median of 5.8. Females starting with 4.8 going all the way up to 6.1 with a median of 5.6. Now you can see by looking at this, hey, looks like there is a difference in the distribution of heights for males and females. And to notice that, you always use box plot. Okay, I'm going to rub them off because that's put under bar chart, which is not true. So this is a box plot. Now, bar chart, two-dimensional. We are going to plot 2 into the bar chart. So this is males and these are females. So we have, let's say, 600 males and 400 females in our data. How many, thinking of the Titanic data set, out of the 600 males, how many have survived the crash? And out of the 400 males that 400 females we have, how many have survived the crash? Now, this is going to tell us that the people have survived, and this is called as legend, which can help to understand the data. And this means the person did not survive. Now, look at the number of survivals in male group, very small. Look at the number of survivals in the female group, more. So that tells us that, hey, in this crash, more females have survived more compared to males. Yeah, we know that, that's a fact, right? So is there a difference in the ratios of survival between males and females in the Titanic disaster? If you have to know that, you can simply plot this bar chart. This is one dimension and this is another dimension. So this clearly tells you that, yes, there is a difference between the ratios of people survived between males and females. So that's a bar chart for two-dimensional. And finally, scatter plot. Scatter plot is between two continuous variables, two numeric variables. Let's say we have X and we have Y. So this is your X and this is your Y. Let's say this is height and this is weight of the individuals. Now, is there a relationship between height and weight of individuals? Okay, if we try to collect the data of few individuals and plot them, this is how it would look like. Each dot here is representing an individual. As height is increasing, weight is also increasing. So there is definitely a relationship between height and weight. So this type of relations are measured using correlation in statistics. So this is called as Pearson's correlation coefficient. So to see if there is a relationship between two continuous variables, we use this Pearson's correlation coefficient, generally represented by R square. Then this is going to be this plot, a scatter plot between X and Y, can easily reveal what would be the relationship between X and Y. For that example, if we take odometer reading and resale price of the car, now as the odometer reading is increasing, resale prices of the car would be decreasing. So if you look at the relationship, odometer reading is increasing, price is decreasing. This is called as negative relationship, negative correlation. When one is increasing, other is decreasing, that's called as negative correlation. When one is increasing, other is also increasing, that's called as positive correlation or positive relationship. When we measure this relationship with our correlation coefficient R square, it gives you a value between -1 to +1. Close to +1, positive correlation. Close to -1, negative correlation. Close to 0, no relation. Okay. Try to make a note of correlation and try to read more about it, so you would understand how correlation can be used as a measure of relationship between two continuous variables, two numeric variables. And the most advanced charts, we call them as multi-dimensional plots. These are very tricky. It has to be built using a lot of technical dependencies. I would not touch multi-dimensional plots here. So far, we have only discussed about what type of plots to use with one-dimensional, one variable, two-dimensional, two variables. And these plots are not the only ones. It's not just limited to this. We have a lot more plots which can try to help us infer the data, but I'm just limiting to this because of the time that we have. Now, let's see how do we produce all of these plots in Python quickly. Then we go to linear regression because we need more time and I have to spend more time there. Okay, you're talking about there was a question on classification. We are not yet there. When we go to the classification, maybe tomorrow I will answer this question. I'll hold on because I do not want to deviate at this time. It would take some time out of this to explain that. Okay, yeah, but I'll definitely do that along with classification tomorrow. And SVC, you mean to talk about support vector classifier, which is part of support vector machines. That's a very, very advanced algorithm. You probably, if you know that, it's good, but I would not talk about support vector machines in this particular workshop. Now, let's try to build them. Let's take one column at a time. I'm going all the way up to add a few more things over here. Import, no, not import. This is another way of importing. So you have seen importing the entire module at a time. Now we are going to import submodule from matplotlib.pyplot. So matplotlib is a module. And in that module, we have two types of plotting engines available. One is called pyplot. The other one is pylab. Pylab came from the MATLAB features. There is a programming language called MATLAB. You can use that also for your data analysis. So people who are familiar with MATLAB, they prefer to use pylab. But in the field, in most of the data scientists today prefer to use pyplot. So that's why I'm using pyplot. Mistake or as PLT. So this is a submodule that we are importing, not the entire module. I don't want pylab. I'm only interested in pyplot. So I'm just getting my pyplot, and this is the alias that we are giving. import Seaborn as SNS. So this is the most versatile plotting module available in Python, matplotlib. But matplotlib is technically very deep unless you try to understand the anatomy of how plottings generally work, how Python is trying to manipulate the data behind the scenes to generate the plots. Matplotlib would be difficult to get on with. Another version built on top of matplotlib, Seaborn. Without matplotlib, Seaborn is nothing. So Seaborn is a wrapper built on top of your matplotlib, which makes building plots and charts very easy, very fast, very quick. Okay, so that's why we are going to use Seaborn. And when we are importing anything, any type of module, we import all of the modules at the top of the code. And this is a programming practice. I can put this line at the end somewhere in between the code, but that's not allowed. We allowed, but as a programming standard, we don't like that, right? So any library, any module that you are using should be there at the top section of your code. And we added these two modules. We are going to use them now to build our plots. Now let's quickly build a couple of them, and then I'll jump on to the next use case. SNS dot, okay, SNS is the alias that we have given for Seaborn, so SNS dot. Now, there are different functions for different types of plots. So now we need to know what type of plot we are going to produce. SNS dot, let's say, scatter plot. And did you see the moment I typed SCAT and hit tab, notebook has completed that code. I don't even have to type that completely. So that's the help that you generally get using the notebooks. Now, I don't know what this scatter plot function does on SNS. I have to read about it. I need an example to understand. You can press Shift Tab, go through the documentation available for it, and you would get to know about it. Now, I have a couple of columns here, which is displacement. I'm going to use displacement. It's called engine displacement, typically measured as CC, 2000 CC engine, 1800 CC engine, right? So that's what displacement is all about. Then I am going to compare displacement versus the city mileage, and the data frame name is going to be my df2. So that's the name, and this is the name of the data frame, and these are the columns. This column will be there on x-axis, and this column will be there on y-axis. And displacement is a number, city is also a number. These are continuous variables. That's the reason I chose a scatter plot. Now, once we run this, beautiful, within this, it has produced the plot. So it did not produce plot somewhere else so that you have to go and take a look at it. It just placed the plot right next below it. Now, look at the points. As displacement is increasing, the city mileage is decreasing, and you could see a negative relationship. So you have a slope that is downwards. So there is a negative relationship between the displacement and the city. If displacement increases, that means the engine capacity increases, the CC of the engine increases. Of course, bigger engines will consume more fuel to produce more torque. That's why the mileage would be on the lower side. So this is the domain knowledge part, and you can understand this by exploring the data. Now, is there a relationship between displacement and city? Yes, very much. Next, SNS dot count plot. So count plot is used with discrete data, one-dimensional discrete data. Now x is equal to, we have a variable called class, and in that I want to know what is the number of vehicles in each of these class. Compact, maybe around 48 cars. SUV, maybe little over 60 cars. Two-seater, very less, maybe around 5 cars, right? So the heights of the bars here reflect how many observations belong to this. And look at the beauty of this plot. We just wrote a simple line of code. We did not choose any color palettes. We did not give anything, any more instructions to it. And Seaborn has done a beautiful job in getting you a colorful plot. And that's the power of data analytics tools like Python and R. To produce this type of plots in other programming languages, it would be taking you a lot of time and effort. Now, let's try to increase this in one more dimension. So this is one dimension. There's only one dimension here. That dimension is on the x-axis. Now, SNS dot count plot. On the x-axis, we are still going to give class, and on hue, I am going to give the drive type DRV, and data is equal to my DF2. Now you get, okay, let me change this. George is equal to false. I know the pace that I am going, it would be really difficult for people who are at a beginning stage to understand, because you do not probably understand what all these arguments are, what they does. That's where I want all of you to spend your time. Look at the name of the plot. It clearly says count plot. So it's going to get you frequency counts and make a plot based on the frequency counts. Then you look into the plot, get the help by pressing the shift tab. Look at each argument, look at the definition of each argument, what values it can take, how we can pass values to it, and you get those beautiful plots. Now let's try to understand this. Compact. In compact, we have two colors, this saffron and then the blue. Compacts are actually smaller cars. Think of them as our hatchbacks. In compacts, you probably see a lot of front wheel drive types. There are three mounting systems that generally people use in automobile. So front wheel drive, four wheel drive, rear wheel drive. Most of the compacts have front wheel drive and few of them has four wheel drive. Look at the SUV. SUVs are very big vehicles, heavy vehicles. They have to produce a lot of torque. Now, SUVs are mostly given four-wheel drive type, of course, to produce the very strong torque. And some of them have been given rear-wheel drive type, no front-wheel drive type at all in SUV. Look at the pickups. Pickups are trucks. If you are familiar with concepts of trucks, GMC, you have, okay, in India you have Isuzu, which makes trucks. So there is a cabin and there is an extension to it, etc. Right? So these are the pickup vehicles, and all of them are four-wheel drive type, because these vehicles are heavy, and that's the reason they have to have produce very high torque, and that's why it has to have a four-wheel drive type. Now, if I have stared at this data set by printing it, maybe for 4 hours, I would not have realized this information. a simple plot with a single line of code has revealed that insight hidden in the data. So this is exactly what people call as data insights. Now, most of you might question me, if I am an automobile engineer, if I am a mechanical engineer, I know all this stuff. Why do I have to do it? To know this stuff, you have to be a mechanical engineer. And without being a mechanical engineer, by just spending 10 minutes of our time doing data analysis, we would be able to figure it out. And if this is a healthcare data, I'm not a physician to know everything about healthcare data. But if I do my data analysis in the most appropriate manner, I would definitely get the hidden insights in the data revealed easily. Okay, so that's the power of data visualizations. I would continue with data visualizations, but along with the concept of linear regression. So let's start with linear regression. So we go back here, and we try to add a new Python 3 code, and let's name this as linear rig, whatever the name that you can give. Demo on linear regression. I want to make sure anybody reading it later should not have any problem understanding this. So this is a markdown. First, import pandas as PD, import numpy as np, from matplotlib.pyplot, sorry, again, import matplotlib.pyplot as plt, import cborn as SNS. You have seen all of this already. Now comes our magic package, scikit-learn. Import sklearn. Instead of importing all the sklearn is a very big module. It has a lot of them. I do not want to get all of them, so I'm going to do this from sklearn.linear. So linear is a submodule as part of sklearn. Import linear regression. From sklearn dot model underscore selection, import train test split. From sklearn dot metrics, import mean absolute error and mean squared error. So these are those steps. These are the functions that would help us to perform linear regression. And what happened? Okay, so this will help us to build the linear regression. This will help us to divide the data randomly into train and test. You remember our first class, we want to randomly separate data into train and test. And these ones will compute the error metrics for us. After building the model, if we have to know how good the model is, we have to use these error metrics. Okay, fine. Data is equal to, I'm going to use a data set that's already present here. So you can take a look at this. This is how the data is. And we are going to use this data to create a linear regression model. How to read the data? pd.read_csv, which we have done that. And this is the name of the file. Done. Data.shape. Let's see what's the size of it. We have 414 records and 8 columns. I purposefully chose a small data set because my intention is to show you how to perform it rather than bringing in a lot of complexity, because this is probably the very first model that you might see. Data.head, so that you will understand what data it is. Okay. First column says number. I think this is ID number. Ignore. This is not going to be useful. Second column says transaction date. Third column says house age. Fourth column says distance to the nearest station. Number of convenience stores. Latitude, longitude, and unit price in that particular area, maybe per SFT or maybe per something. I don't know what would be the measure of it. Okay. Now, you can clearly see, depending on this, we want to predict what would be the price per SFT in that particular area. So this is the prediction. This is the target that we have to predict, and these are all going to be our input variables. Data.columns is equal to, I don't like these column names, especially when there are spaces given in the column names. It's not a really good programming standard. Never ever have space in any of the namings. So I am going to change these. First one, I am going to give my own name ID. Second one is date, whatever be the date. Third one is age. Fourth one is distance from the nearest station. To make it convenient, I'm just going to use distance. Number of stores, then latitude, comma, longitude, then price, which is going to be our target variable. Okay. Now, these are the names I have assigned to our data frame. Now, if you look at data.head now, the old names are gone. The clean names, ID, date, age, distance, now it looks cleaner, easy to handle. And especially when I want to do something on one column, one variable, imagine typing all of this as a column name. That's stupidity, right? So that's the reason having proper and easy to understand column names is also important. Now, let's start our EDA. First, are there any missing values in this data? Data.isNull.sum. Wow. Clean data, no missing values at all. If there was any missing value, I would have imputed, but there was no missing value, so I would ignore. The next step is data analysis, or you call this as EDA. This is to understand the relationship between your variables. Like, is ID related with this price? ID is just a unique identifier. How would it have any type of relationship with the price? Date. Oh, I don't, when this particular observation is created, and this would have nothing to do with price. So these two columns, ID and date, we would ignore. There could be some valid information in date. Why? Price is going to increase by time also. in 2012 price would be less, in 2013 price would be more, depending on the same locality. Latitude, longitude is same. 2013 price is more, 2012 price could be less. So this is the understanding of the data that we need. And these variables that exhibit strong relationship with price, those are the ones which are going to be our input variables. ID here is not at all an input variable. Why? Price of AS per SFT will not depend on this ID. It would depend on the age of the building. It would depend on the distance from the metro station. It would depend on the number of nearest grocery stores around it. What is the latitude, longitude, but it would not depend on ID. So ID is not going to be useful at all for us. In my analysis, I am going to select these columns. The columns from age, the columns from age to price. I am going to ignore the columns ID and date from my analysis because I'm not going to use them. New data is equal to, I'm creating a new data frame, data, and only these calls. I'm not going to use other calls, right? So now if you see new data dot head, we would see only few columns, these columns, and these are good enough for me for the analysis. Next, let's try some EDA. Let's try some visualization to understand the relationship between columns. I want to see if there is a relationship between age and price. It should be, right? More the age, lesser the price. That's how it should be. Now, is it true? Let's try to understand this with SNS. SNS dot, what would be the plot here? Age is a continuous variable. Price is also a continuous variable. So scatter plot. X is equal to age is sensitive all the time, and Y is equal to price. On x-axis take age and y-axis take price, and then data is equal to new data. Semicolon is not required in Python. It is actually the terminator, but not required. But here, especially when we are building visualizations, we put that semicolon. Without the semicolon, it prints the object information and the memory location. It looks odd. A lot of people, when they see this, hey, what is this? There is nothing that you try to understand. It's just the memory location and the object information, and you would not be able to understand anything from it. So to avoid that, we put a semicolon. Now that object information is not printed anymore. So this is the plot that it has produced. Now, if you observe, as age is increasing, slowly the price is coming down, but at some point in time, when age is very high, you would still see the price per SFT is also high. Maybe some vintage buildings would fetch more price than the regular buildings. So that's why you probably see some higher price over here. But overall, there is a negative correlation between age and price. So to know more about these correlations, we could simply say, apply the function car on the entire data at a time. Now it computes the correlation with all the variables. Ignore the diagonal variables. It is correlation age with age. Age and age is same. So obviously correlation will be 1. Correlation between age and price, minus 0.21. I told you this is going to be a negative relation, and it is close to minus 0.2, close to 0. So a very weak relation. Some of them could have strong relation. Look at here. Distance from the metro station and the price has a negative correlation of minus 0.67, and minus 0.67 is very close to -1. It's a negative correlation, but a strong correlation. Far away from the metro station, prices are less. Closer to the metro station, prices are more. That's what the negative relationship means. People raising their hand, please type your questions on the chat window. Stores nearby, number of stores, more number of stores, higher price, lesser number of stores, lesser price. So this is a strong correlation, 0.57, but positive side. There is no negative symbol. So more the stores, more the price. Latitude and longitude, both of them has 0.54, 0.52. This could be because of the locality. Maybe latitude higher is probably the metro side of the city. Latitude lower is the rural side of it. And that's the reason you would see this. Now, age is having some relation with price. Distance is having very strong negative relationship. Stores is having strong positive relationship. Latitude is having strong positive relationship. Longitude is also having strong positive relationship. So we can use all of these variables in our analysis, in our prediction. Let's say if there is a variable with almost having a correlation of 0 with price, that is a useless variable. There is no relationship between that variable and price. So probably we do not want to consider that in our analysis. So EDA is going to help you in selecting the right input variables that can predict your target variable. Only if there is a relationship between the input variable and the target variable, using that variable, we can predict the target variable. If there is no relationship at all, you cannot use that variable in your prediction. So that is the reason your EDA, the EDA that we are going to perform here, is mainly to select variables into your prediction. So that's the reason it's also called as variable selection process. Out of all the variables that we have, we are going to select some of the variables that has some impact on your target variable. Luckily, in this data set, there is no discrete data. There is no character data. If we have character data, we have to deal with it slightly differently. Tomorrow, we will see some character data in the logistic regression. Let's, for now, continue with this. Another way to look at this is called as pair plot on data. It would take some time. See, now you see a star here. It is still under execution. Once this star changes to a number, that means the execution is completed. So a pair plot is a plot of one variable with rest of the variables. Age versus age. Age versus age doesn't make any sense. So this is the histogram of the age. If you remember, we just discussed about histogram, which tries to tell you the distribution, and this is not following that shape of a bell curve. So this is not following normal distribution. Age versus the second column, distance. Age and distance will not have any type of relationship, so ignore. Age and stores will not also have any type of relationship. Age and target variable has some sort of negative relationship. Age and price having negative relationship. Distance and price have negative relationship. Stores has positive relationship, latitude, longitude, and this is the histogram of the price. And this is slightly closer to that normal distribution. Looks like it is closer to that bell shape, bell curve, right? So we can say that, okay, price is kind of following normal distribution. Now, instead of producing these plots one by one, age versus price, age versus distance versus price, stores versus price, latitude, longitude versus price, simply say pair plot on the entire data. It just produces a grid, and through the grid you can see the relationship between one variable with rest all of the variables. That's very powerful and very easy. Okay. Any audio issues? Are you able to hear me? Okay. Looks like these are happening because of some network issues here and there. It could be a network issue from your side, or it could be a bandwidth issue, etc. Yeah, hopefully it would be back very soon. Next, I'm done with my EDA. I know what variables I'm going to use. I would probably jump on to building our very first prediction model. Going to build our very first prediction model. Okay. Yeah. So before we build our very first prediction model, we have to separate our data into train portion and test portion, 80% into train and 20% into test. So I'm going to split the data like this. Target is equal to, and what's our target variable? Our target variable is price. So price is our target variable. So I'm going to select price into a new variable called target here. And can we share attachment in this, in the chat? Yeah, attachment is shared. You can take, if you want to practice, you can practice along with me. Now, our input variables, I'm calling this as input X variables. New data, what are our input X variables? Except price, rest all of them are our input X variables. So these ones. So let's try to select them. So we have separated our target variable and separated our input variables. Now the data frame was like this before. We have one big data frame which has a lot of input variables. These are all our X and this was our Y. Now we did break this into two portions. So this is our input X and this is our target here. And you know why, you will understand why we did it in a couple of minutes. X underscore train, comma, Y underscore train, comma, X underscore test, Y underscore train, comma, Y underscore test. I'm going to create these four objects. X underscore train, X underscore test, Y underscore train, and Y underscore test in one single line of code. And this is another good thing about Python. X comma Y comma Z is equal to 10 comma 20 comma 30. Now it automatically takes 10 into X, 20 into Y, 30 into Z. So you don't have to write them in 3 different steps. So that's what we are going to leverage here. we are going to create all these objects by using this function train test split. Of course, any function, you would always try to get the help, understand what it does. I know what arguments are there and how it actually works. So it takes input X, the input data set, and then the target which is going to have the target variable, test underscore size is equal to 0.2. That means 20% of the data should randomly go into X underscore test. 80% of the data should randomly go into X underscore train. That's from inputs. The same 20% elements should go into test, and the remaining 80% should go into train. And one more argument, random underscore state is equal to 1. So this random underscore state is a seed. If you are familiar with the concept of random number generation, every computer has an inbuilt algorithm called as a random number generator. And each time when you use a random number generator, they produce different results. If you want to get same result, we want to fix the seed for the random number generator. And this is the seed. And this one has no meaning. You can give 1, you can give 2, you can give 3, doesn't really matter. You can give 9. It doesn't have to be a single number. It can be a it can be any number. It can be 3-digit, it can be 4-digit. Okay. Now in this single step, we have created X underscore train, print X underscore train dot shape, print X underscore test dot shape, size. Oops. We have 331 rows in training and 83 rows in the test. So that's the 80%, 20% split. You can also look at target. Target train is Y underscore train dot shape. Target. And on training, target will have only one column, so that's why it is not printing anything here. It has 331 elements and it has 83 elements. So this single step took care of all our random train and test split. Fine, we have our train and test data sets ready. We should be building our regression model very soon. Linear regression. So this is the function. You want to know more about it? Can dive into this. I know what it does. Linear regression dot fit. So this is a function call, and we are probably like it's like initializing it. Now to learn from the data, we need to pass the data. So this step, this fit step is called the training. In this, we are going to say, hey, x underscore train, this is my input variables, and this is my target variable. You learn from it. Okay, so we are asking the linear regression algorithm, learn how to predict y underscore train using x underscore train, and that's all done. It is ready. It has learned already. Now it can make predictions on your test data set. Let's see how the predictions would look like. Predictions is equal to, what is the name of the object that we have trained? LR dot predict, and predict using x underscore test. And here we are not going to give y underscore test. Y underscore test we would be using for assessment. So we are just giving x underscore test. Hey, show me what you have learned by predicting using x underscore test. It has given you predictions. Now, if you want to add the predictions, let's say these are the predictions. For the first observation, it predicted the value as 31. For the second observation, it predicted the value as 35. So you can compare them with the y underscore test. For the first observation, the value is 34.2. What did we predict? 31.1. For the second observation, value is 47.3. We predicted 45.8. They look close. Some error is definitely there, but they just look close. This is index. Don't worry about it. So ignore this. This is the actual values. Now, how do we know if the model is really making good predictions? We have to compute our error matrix. So to compute our error matrix, error is equal to, what is our error? Y underscore test minus predictions. So this is the error. So we computed the error for each and every observation. Now I want to compute the print mean absolute error. It takes two arguments, y underscore test, which is the actual values, predictions, this is our predictions, and it's going to print mean absolute error for us. So this is just a note to understand what we are printing. Print mean squared error. Whoever is raising the hand, please type your question. I'll answer them. Again, y underscore test, comma, predictions. Our mean absolute error is 6.7. That means on average, we are making an error of 6.7. Mean squared error is 140. This is on squared term. We want to bring into linear term. So let's add one more error metric. Root mean squared error. So we are going to apply square root on this. np.sqrt. Sqrt is a function which is actually available in Python. It would try to compute the square root of this value and print this. So our root mean squared value is 11. And these errors are slightly difficult to judge from. So that is why we need something called as map. So let us write our own function and name it as map. It is going to take two arguments, actuals and predictions. So this is how you write your own functions in Python. I am writing a function called map. It takes two arguments as input. The arguments are actuals and predictions. Error is equal to difference between actuals minus predictions. Then we want to take the absolute value of it. So ABS of this. So I'm going to make this as absolute error. Absolute error is this. Percentage error. Percentage error is equal to ABS error divided by actuals. Error in terms of your actual values. So that would give you a proportion. Convert that into a percentage 100. And we would get this as a percentage error for each and every observation. We want to aggregate it. So map is equal to np.mean of percentage error and return. I don't want all of them, return only map. Now we have built a function print mean absolute percentage error is equal to map. It takes two arguments, actuals. What is actuals? Y underscore test. Predictions. Our predictions are named as pred, and it printed our absolute percentage error as 16%. That means on average, we are making an error of 16% when we predicted the per square feet prices of houses. 16% error is definitely on the higher side. We would probably want to have something that is below 10%. We can improve it. How we can improve it? Remember, we did not use the column date, and date also has some information. Higher the year, maybe prices has increased. So we haven't given that information to learn from. So if we could transform that date a little bit and give the date also as an input, then your error might decrease further. Okay, so take the data set and try to do that transformation. Only take the first four parts, year part, ignore this one, and from you pass this as an additional input variable to the model and see if the model has improved. And this one here, the two statements that we have built here is the magic one. This is where the learning is happening. And from this learning, it has made these predictions, and we definitely have performed on average with a percentage error of 16% is not bad at all to start with. Okay. Not map is not a predefined function. We are writing that function. So we are defining the function here. So these are called user defined functions. And this is how you create a user defined function. A function will take arguments. Arguments are your inputs. From that arguments, you are making some computations. And whatever you want as the final output, we are only returning it. So this is how to write user defined functions in Python. Okay, there is no inbuilt function for map, so that's why I wrote my user defined function. Okay, yeah, let me see if there are any questions. Other questions. Type of y-test. Y-test is a pandas series because it has only one column, so you can type of y underscore test. So it's going to be a pandas series. One column is considered as a series. More than one column is considered as a data frame in pandas. Please type your questions. Even if you raise your hand, I'll not be able to talk to you. Now comes the most important part. Find hardly some, probably maybe around 20 lines of code. We have built a prediction model. We have learned from the historical data. We have learned from the training data. We have predicted using that model. And we looked at the error metrics, and the error metrics are kind of satisfactory. 16% is not a big deal. We have to bring it even further down, but for a first model, this is definitely a great start. Now, what happened in this statement? That's more important. That's where all the data science is going to come. Okay, so let's try to understand what is behind the scenes playing here when we write these two statements. How is it trying to learn, then how is it making predictions? So that's very, very important. So actuals minus predictions means for every observation, for first observation, this is your prediction, this is your actual. So 34.2 minus 31.1, and that's what is going to get printed. You can see, and so 34.2 minus 31.1, 3.03. So this is nothing but error for each observation. For each observation, we have an error, and some of the errors are positive and some of the errors are negative. It's not summation, it's going to give you the difference between actual and prediction. Now look at the function that we have wrote. Here we get the difference. We do not want the sign, so we are converting them to absolute values. So this is absolute error. For each absolute error, we are converting it into a ratio of its actual number. So that is going to be called as percentage error. And we get percentage error for each observation, and we want to aggregate it by taking the average, mean. So that's why taking the mean of all errors, that's what we call as MAPE, mean, absolute, percentage error, and finally it returns MAPE. Got it? Fine. Now let's look at the beauty. What is there behind those two lines of code, and how linear regression is able to learn from it and make predictions. A pair plots, maybe at the end of the session we will again come back to it. Pair plots is definitely a very easy topic. Even if you can search on the internet, you will be able to understand, but this one is very important. How does linear regression work? What is the science behind it? So to start with, let us start with something called as simple linear regression. Then we would bring in the complexity later. Okay. So in a simple linear regression, we will have only one input variable. So that's why I am going to use a simple linear regression. So this is your X and this is your Y, and only one input variable X and one input variable Y, our target variable Y. Let's say this is height. Given the height of a person, can we try to predict the weight of a person? So that's what we are trying to do. Now, if you take few observations and plot those few observations, let's say these few observations looks like this. Now, these are all the points. Now, if we look at the line that probably is the best line that can fit among these points, which is a linear line, the line that satisfies with most of the points here, and we represent this line as y is equal to, or y hat is equal to mx plus c, where m is nothing but the slope of the line and c is nothing but the intercept. Okay, so indirectly, what linear regression means is we are trying to represent the relationship between x and y with the form of a linear equation. So y is equal to mx plus c. We write this in a slightly different form. Y hat is equal to beta naught plus beta 1 x1 or x, because we have only one input variable. So it's just going to be like this. Fine. Let's say we have some data and we plot the data like this. So the data we have is 1, 2. So this is x and this is your y. 2, 3 and 4, 7 and 5, 5. So this is our data. So this is your 1, this is 2, this is 3, this is 4, this is 5, and this is your 1, 2, 3, 4, 5, 6, 7. First observation is 1, 2. So that's this observation. Second observation is 2, 3. So that's this observation. Fourth observation is 4, 7. So this is 4 and this is your 7 somewhere over here. And fifth observation is 5, 5. So this is your 5, 5. Now, these are the points. Now, what is the best line that can explain these points? What is the best linear line that can explain these points? And that's starts with an assumption. The assumption is we assume that the relation between x and y is linear. So in linear regression, we start with the assumption. And if this assumption is not satisfied, we would not be able to use linear regression. So we are assuming that the relationship between x and y is linear. You might have done this in a lot of your lab exercises in your engineering, right? You conduct some experiment and you take the note down of the readings. You try to put them on a graph paper, and once you have them on a graph paper, you try to draw a line, the best line among those points. In simple words, you could probably say the best line is the one that touches the maximum number of points. So that's a way to find out the best line. So now you are going to use this best line to explain the relationship between the input variable x and the target variable y. So probably you write this line as y is equal to beta naught plus beta 1 x. Beta naught is this, wherever it touches your y axis, that's called the y intercept. And slope beta 1 is going to be the difference of, let's say this is x1 y1 and this is x2 y2. You take y2 minus y1 divided by x2 minus x1. So that's the best fit line, and you get the values of beta naught and beta 1. Now we have explained the relationship between x and y with the help of a linear equation. Now you know the value of x. You already know the value of beta naught and beta 1. You can predict the value of y. You can guess the value of y. So for example, if x is equal to 3, then our prediction y is wherever it touches this line. And let's say our prediction in this case could be 4.5. So if x is equal to 3, our prediction y is going to be 4.5. That's what linear regression is all about. But it's not as simple as this. Why? There is a question. Now, how did we find out this best line? So see here, this is the line. We are calling this as the best line. How did we find this best line? How did Python find this best line? If you have a graph paper, maybe you can do this. You can try to plot them. You can try to get a line that you think is the best line. and try to get the slope and the y-intercept, and you can do it. But Python is not really doing all of this. Python is doing a amazing job behind the scenes, and that's where it gets a little tricky. For us, the best line, we define the best line as line that is nearest to all the observations. That's how we define the best line. So we want to find out a line that is nearest to all the observations. Now, what is the line that is nearest to all the observation? So there are a lot of possible lines. So this is a line, this is a line among these points, this is a line among these points. Now, which is the line that is nearest to most of the points? How do you decide? Simply do this. Find out the difference between the point to the line. Some of the differences could be positive, some of the differences could be negative. Okay, so find out the difference between the point to each line and sum them up. Now, the one that gives you the least amount of differences, that is the best line. That's one way to do it. But the problem is, let's say this is a difference of -4 and this is a difference of +4. If we try to sum it up, it becomes 0. So the negative values and the positive values are going to impact our analysis a little bit. So instead of summing them as it is, what we are going to do is we are going to square the differences and sum them up. So it's not just sum of differences, we are going to take the sum of squared differences. And the line that gives the least value for the sum of squared differences is the best fit line. And that is why the principle behind this linear regression is called as ordinary least squares or sum of least squares. Okay, so if someone says, hey, what is the principle behind the linear regression? It is trying to find out the best fit line using sum of least squares or ordinary least squares. Now come back to this data. So there are multiple possible lines and we can draw multiple possible lines here, and we can compute what is the best line that is having the least value of it and pick the best line. And that's also not computationally feasible, right? If there are 1,000 points like this and you can probably draw like 1,000 lines between them, you cannot draw each line, compute the difference between the line and the point, square them, sum them up, and see if it is the least or not. So we are going to use some mathematical approach to figure out that least line. Now, for this data, we want to find out the line that satisfies this. That is, we are predicting it as y hat is equal to beta naught plus beta 1 x. So this is the line. Now, we want this line to be the best line if it satisfies this condition. That is, for the first observation. For the first observation, beta naught plus beta 1. What is the value of x? X value is 1. And what is the value of y? Y is 2. Minus 2 whole square plus second observation. Beta naught plus beta 1 into 2 minus 3 whole square plus beta naught plus beta 1 into 4 minus 7 whole square plus beta naught plus beta 1 into 5 minus 5 whole square. So this is nothing but the sum of squared differences. And we want this to be as small as possible. In an ideal case, this should be 0. So we have a function, a quadratic function, which want to take a value of 0 or a smallest possible value. Now, this is a function which is in the form of f of beta naught comma beta 1. So we want to find out the values of beta naught and beta 1 in such a way that this function takes the minimum possible value. And how to do that? Maxima, minima, calculus, minimization. Let us try to minimize this equation and try to find the values of beta naught and beta 1 in such a way that it is going to be the least value for this function, and this is called as cost function. So in machine learning, the learning happens with the help of a cost function. For linear regression, the cost function is called as ordinary least squares. But we have two unknowns here. So how do we do maxima, minima? Minimization, especially by taking the first order derivative. So we have to take the first order derivative of this, but we have two unknowns. So we are going to take the first order derivatives, partial derivatives, dou by dou beta naught, dou by dou beta 1. So if we derive this, of course, don't worry, I'm not going to derive. I'm not going to take you through the calculus class again. I know people would get really bored. 95 beta 1 is equal to 138. So this is one equation that we get. And the another equation is 5 into beta naught plus 19 into beta 1 is equal to 28. So this is another equation that we get. We have got two equations with two unknowns. Now you can solve these two equations with these two unknowns to find the values of beta naught and beta 1. And how do you do that? There are many methods. One, the popular method called as elimination method. You add or subtract these equations by multiplying it with a scalar in such a way that one of the element would be removed. Find out the value of beta 1, then place the value of beta 1 in one of the equations to find out the values of beta naught. So this is the linear algebra that we have learned in our school days. Another way, matrix method. So this is in the form of a matrix: 19, 95, 5, 19, beta naught and beta 1 is equal to 138, 28. So if you send it other side, it becomes inverse, multiply it, you get your beta naught and beta 1, right? Fine. If we started with a simple linear regression, we have only one input variable and one target variable, and there are n number of possible lines that can be possible among these data points. We assumed that line is an imaginary line which has the shape of beta naught and beta 1x, and we substituted that into our data. We want that line in a form that this equation, this cost function, takes the minimum possible value. So that's the reason we applied calculus. We want to minimize this cost function in such a way that this cost function takes the minimum possible value. So we want to find out the beta naught and beta 1 values that gives the least value for this. So if we substitute these beta naught and beta 1 values into this equation, those are the values. I think the beta, the beta 1 is going to be 79 by 57 something, and beta naught is going to be 1 by 3. So these are the values which gives the minimum value for this function. Any other value would give a value higher than what we get for this. So that is why we are going with minimization. But there are a lot of challenges here. Why? Because we are going with only one input variable, we have beta naught and beta 1x, which is probably 2 unknowns, but there could be situations where we have 10 input variables. Then you write your prediction like this: beta naught plus beta 1x1 plus beta 2x2 all the way up to beta nxn or beta mxn. Now you have so many unknowns. So now you apply your partial derivatives, dou by dou beta naught, dou by dou beta 1, dou by dou beta 2, so on. And you probably get, let's say, 10 partial differential equations. Not one, you have got 10. Now, how do you solve 10 equations? If it is 2 equations, yes, we could easily solve them. If we have 10 equations, solving them through elimination method is very, very difficult. Imagine eliminating one at a time, one at a time, one at a time. You need to eliminate 9 elements, finally reach out to one of the values, and then replace them back one by one to find out the rest of the values. If you do that on a paper, it would take 1 or 2 days to do that. And to avoid that, we are going to use some of the iterative methods. What are the iterative methods that you came across to solve equations? You have something called as Gauss-Seidel method. You have Newton-Raphson method. Of course, these are all people, we just read it as part of our engineering mathematics, but we don't really think that people use it anywhere. Data science is a field where, starting from the 5th class mathematics all the way up to your engineering 5 mathematics, everything is used behind the scenes. Statistics, for algebra, ratios and proportions, calculus, probability, everything comes into the picture here. Nobody would have thought that linear programming iteration methods would be so useful. But imagine if you have to deal with millions of observations and hundreds of columns. Your equation could have 101 unknowns. You are trying to solve 101 equations at a time. It would be literally impossible to do that if we don't have these type of automatic iterative selection methods. What do? Randomly initialize all these values, find out the derivative, find out which way they have to go, and we would be able to reach out to a value at some point in time where this whole cost function takes the minimum possible value. That's the beauty of data science. You might just think, okay, if I write these 2 lines of code here, linear regression, learn from this data, it is done. But what happens behind these 2 lines of code takes really a lot of time and effort to understand. Just behind the 2 lines of code, you have so much amount of mathematics, so much amount of science involved in it. And now people, if someone asks, why do we have to use Python? This is the reason. Imagine if that 2 lines of code is not capable of doing this, and you have to do all of these calculations on your own by writing programs for them. This could be an effort of 1 month. And that's really the power of Python and the power of modules that we have in Python. With a very simple 4-5 lines of code, we can easily try to learn from the historical data and make predictions into the future and see how good those predictions are. But if you don't understand the effort that went into in building those modules, imagine people writing code for all of these behind the scenes. So indirectly, you are substituting the data that you have into this cost function. What data you have? X and Y. X is 1, 2, 4, 5. Y is 2, 3, 0.75. So you substituted that data into this cast function, and you want to learn through this cast function in such a way that when you find out the values of beta naught and beta 1, this whole cast function takes the minimum possible value. That is why the name ordinary least squares or sum of least squares. So what do? We have to take the help of calculus. We are going to do minimization. Find out the values of beta naught and beta 1 in such a way that it takes the minimum possible value for this equation. So to perform minimization, we need derivative, first order derivative. But there are two unknowns here, beta naught and beta 1. So we cannot go with the regular derivative. We have to go with the partial derivative. So the partial derivatives for this is this. And now if you solve this equation, you find out the values of beta naught and beta 1. That gives the minimum value for this equation. Perfect. Now, if you have more of them, you would get more variables into your model. Your equation becomes lengthy, and you would get many partial differential equations. You have to solve them. That's going to be a very tedious effort. To take the effort down, we go with the iterative methods. We use the Newton-Raphson Gauss-Seidel iterative methods behind the scenes to solve it. This is not the only approach. You can use matrix inversion method. You can use something called as gradient descent method. One more very popular and latest technique, right? But behind the scenes, there has to be a cast function which helps you to learn from the historical data. You substitute your data, your training data that you have into this cast function. Through this cast function, your learning is happening. Every algorithm will have a different cast function. And if you don't understand how the cast function is working, you will not understand what your algorithm is actually going to do behind the scenes, right? Now, when we built the model, what happened here is it computed the intercept for you. This is the intercept for this model. It computed the coefficient for you. So this is the coefficient for the first variable, second variable, third variable, fourth variable, fifth variable. Now it's like writing an equation. My predicted value y hat is equal to, this is your intercept, the constant, minus 2 times or 2.6 into 10 to the power of minus 1 times h, minus 3.6 into this, plus into the distance, into latitude, into longitude. So that's like writing your final equation. And you don't have to write it. Python will be taking care of it. In this step here, Python is using that equation to make predictions on your test data set. But if you have to use this equation somewhere else, like you want to build a web page, and in that web page, user inputs this test data for you. So you build a web page where user gives what is the age of the house, what is the distance from this, how many supermarkets are near. So they enter this information, and from that information, if you have to compute the prediction, then you need this equation. That equation is predicted value is equal to intercept plus this times this coefficient times age, this coefficient times distance, this coefficient times stores, this times latitude, this times longitude. And if you substitute those values, you would get your final prediction. That's how predictive analytics work in data science. Learning from the data is always going to happen through a cast function. You dump your data, the training data, into the cast function. Depending upon the situation, you either maximize it or minimize it. Here, if we have very minimum distance from each point to that line, that is the best line. So that's the reason we want a line that is nearest to all the observations. So we want the point given by the line and the original value very close to each other. Ideal case, it should be 0. All the points should be there on the line. So we want this cast function to take the least possible value. And that's the reason we are minimizing it. We are trying to find out the values of beta naught and beta 1 in such a way that it takes this, it gives the minimum value for this cast function. Okay. Training data is generally divided into 80-20. The reason is we need more data to learn. Training examples should always be more. So you have more training examples, your learning would be always better. So that's why we always go with more training data. But having said that, it doesn't have to be always 80-20. You can sometimes take 70-30, you can sometimes take 90-10 also. Only thing, more data should be there in your training. Now, when you only have, let's say, 200 observations, you probably take 160, 170 observations into training because your training needs more data, and test it only maybe on 40 or even lesser observations, right? So training should be more and testing should be less. Okay, that's linear regression for you. And people who think that it's all just like writing simple piece of code behind the scenes, you are wrong. There is a lot of scientific concepts involved behind the scenes. Now you go back and appreciate your maths teacher, whoever taught you the probability, whoever taught you the matrix, and then the matrix manipulations, etc. Everything is taking place in here. This is where you really see and use the maths. Okay, I think I answered most of the questions that came in, except that one question which talks about classification, which we will see tomorrow. Any further questions that you have? This is heavy stuff. I do agree. When people hear to this for the first time, they get really overwhelmed by the amount of information there. And that's natural. And people get scary also. Whenever something is having a lot of technicalities in it, it generally scares people. But if you take your step forward, overcome that fear, this will be giving you probably the best time of learning that you could ever have. And you could really get surprised by the depth of this subject every day. You might probably take 1 year, 2 years, but still you would be learning throughout your career as a data scientist. And that's what motivates me, and that's what I love as part of my job. It's not like you are done with something and then you do the same routine, boring task throughout your career next. No, that's not how data science is. It's always going to be a learning exercise where you keep innovating, you keep learning new things.
Sir, thank you, sir. Vijay sir.
Yes, sir. Kiran, sir.
One more wonderful session.
Most welcome, sir. My pleasure.
Yes, sir. I think no more doubts are there. All are giving a feedback as it is a wonderful explanation.
Most welcome. And I really appreciate people with their questions. The more you make this interactive, the more you are going to understand. It has to be interactive. Without having that interaction, you would not learn anything. So don't hesitate to post your questions. The more the questions that you post, that means you are trying to follow. That means you are trying to pay attention and trying to understand the concept. If you understand the concept, this is beautiful, and you would always love it.
Yes, sir. Once again, thank you so much, sir. Again, we'll meet in the tomorrow session.